So, good morning to all of you. Today we are going to cover a very important topic, that is digital to analog and analog to digital converters. This topic is covered under subject digital system design, which is a syllabus of second year EC electronics and communication engineering. I am Sulekha Saxena, assistant professor EC department AKGEC Ghaziabad, and today we are going to cover ADC and DAC converters. We will start from the very basic first topic, that is digital to analog converters. First of all, why we need A to D and D to A converters? Basically, in today's environment, all the electronic devices are digital circuits and process data in digital format, whereas all real world signals are in analog format. So, we require analog to digital and digital to analog converters to process any information through digital system. Means, when we talk about any digital system processing, it needs digital input, whereas all real world signals are in analog format. So, we require A to D converters at the input to convert real world signals to digital format. Then the system or the hardware processes this digital signal and generates this digital output. This digital output is again to be converted to analog form to be understandable by real world environment. So, this is the need of A to D and D to A converters, and different type of hardware exists on date to convert any digital signal to analog and vice versa. We will start from the very first DA converter, that is the logic behind D to A converter. If we consider a D to A converter with 3 digital inputs, with 4 digital inputs, then for 4-bit binary, the total number of levels are 2 to the power 4, that is 16. If we consider 4 digital inputs with as D, C, B, A, with D as MSB and AL as SB, then this DA converter converted into analog output, such that the analog output is proportional to digital input with K as proportionality constant. We will consider an example of how to convert an analog signal to digital. Consider this as an analog signal which is continuous in time as well as amplitude. So first we will convert this signal into discrete, that is discontinuous form. For that, first of all, we break this signal on time axis, that is make it discrete on time axis. For this purpose, we take discrete number of samples, which this process is called as sampling, and remove all other values. We take these values, that is discrete number of samples, and remove all other values. And next, we take the staircase approximation and generate this output, and then encode these values in form of digital signals, the maximum and minimum value into different digital levels based on the size of digital word. For example, if we take a 4-bit input, then the total number of levels will be 2 to the power 4, that is 16. So, the full scale output will be number of steps into step size. Using this staircase approximation, now if we take a 4-bit counter and generate the output, then and 4-bit up counter, then it will count from 0, 1, 2, 3, 2 to the power 4, that is 16 minus 1. So, it counts from 0 to 15. So, the maximum full scale value will be 1, 1, 1, 1 which is equivalent to 15. And hence the final formula for output will be number of steps into step size, that is, in this example we have taken 1 volt. So, for n bit digital to analog converter, the number of levels will be 2 to the power n. For example, for 4 bit, the number of level will be 2 to the power 4, that is, and the number of steps, this is the level and these are the vertical is the steps. So, the number of steps will be 2 to the power n minus 1, that is 15 for 4 bit. Why it's minus 1? Because starting from 0 to 1, 1 step, then 1 to 2, second step. So, the 16 minus first, that is 15 steps. The difference between two levels is a step. So, the full scale output will be number of steps multiplied by step size. Now, the various parameters of DAC which we have to calculate are, first of all, resolution, such as that is step size. It is the smallest output change or the value of one level is called as one resolution. We can also say it as the one increment in digital input is equal to weight of one LSB. So, resolution or step size can also be seen as the full scale voltage minus initial voltage, that is maximum minus minimum voltage upon total number of steps, that is 2 to the power n minus 1. For example, if we take a previous example of 15 volt, then the resolution will be 15 volt minus 0 upon 2 to the power 4 minus 1, that is 15, which is equal to 1 volt, which we have taken here. So, the resolution is maximum voltage minus minimum voltage upon total number of steps, that is 2 to the power n minus 1. Now, we have to calculate the percentage resolution, that is reciprocal of total number of steps is percentage resolution. We can also calculate it by 1 upon total number of steps into 100 or step size upon full scale value into 100. So, better the resolution, the higher is the number of bits required. So, as the number of bits are increasing, number of steps will increase and resolution will be better. So, better resolution requires larger number of bits, that is larger number of small steps and small step size, or we can say the small the step size, the better is the DAC converter. So, for 6 bit DAC, for example, the percentage resolution will be 1 upon 2 to the power 6 minus 1 into 100, that is 1.587%. Whereas, if we increase the number of bits to the make it 12 bit DAC, then the resolution will be 1 upon 2 to the power 12 minus 1 into 100, which comes out to be 0.0244. So, the smaller the percentage resolution, better is the DAC. Now, we take one example of a 6-bit DAC having a step size of 50, and we have to find out the full scale output voltage and percentage resolution. For a 6-bit DAC, the full scale output voltage will be total number of steps, that is 2 to the power n minus 1 into value of one step, that is 50 millivolt, that is 2 to the power 6 minus 1 into 50, 2 to the power 6, that is 64 minus 1. So, 63 into 50, which comes out to be 3.15 volt, and the percentage resolution will be value of one step size, that is 50 millivolt, upon full scale value, that is 3.15 volt multiplied by 100, which comes out to be 1.587 percentage. We will take one more example of a 8-bit DAC. Output voltage is given as 0.05 volt for digital input 1. We can see that it's 1, so it's one step size for 0 to 1, that is 1 step size is equal to 0.05 volt. Find the full scale output. So, the full scale output will be 2 to the power 8 minus 1 multiplied by 0.05. So, 2 to the power 8, that is 256, minus 1, which is 255, multiplied by 0.05, which comes out to be 12.75 volt. And the percentage resolution will be step size divided by full scale value multiplied by 100, which comes out to be, now there is one more question. We have to calculate the output for an input of 0, 0, 1, 0, 1, 0, 1, 0. So, first of all, we will convert this binary value into decimal, which comes out to be 2 to the power 0, 1, 2, 3, 4, 5, that is 2 to the power 5 plus 2 to the power 3 plus 2 to the power 1, that is 32 plus 8 plus 2, which is 42. So, this is the decimal equivalent of this binary number, and to calculate the V out, we have to multiply this decimal value with one step size. So, the output will be 42 multiplied by 0.05, which comes out to be 2.1 volt. So, if we have to calculate the output for any binary input, first of all, we will convert this binary value to decimal equivalent value using weighted sum approach. Then the decimal equivalent value of this digital input is multiplied by one step size to calculate the output for that particular input. So, these are some basic numericals or percentage resolution and output calculation for DAC. Now, we move towards a circuit for DAC. A very basic and important circuit is called as weighted resistor. Here, we take an op-amp which works in non-inverting configuration. Positive input is connected to ground or single pole double throw switch, and negative feedback is used. To give the input, we take the weighted resistors 2 to the power 1, 2 to the power 2R, similarly weights 2 to the power NR for n bit binary input. So, and for binary input, we take the reference voltage negative, that is minus VR, so that the current will come out to be positive. So, in this example, as this terminal is ground, so as Ri is infinite, so point A will also be at 0, and using this equation, I naught is equal to I1 plus I2, I naught is equal to I1 plus I2 plus I3 plus IN. So, the KCL at point A will come out to be I naught equal to I1 plus I2 plus up to IN, where I1 is written as 0 minus of minus VR, that is plus VR upon 2 to the power 2R multiplied by digital input D1. Similarly, I2 is written as VR upon 2 to the power 2R into D2. Then I3 is written as VR upon 2 to the power 3R into D3. And similarly, IN is written as VR upon 2 to the power NR into digital inputs, with DN as LSB and D1 as MSB. So the combined output can be written as VR upon R D1 into 2 to the power minus 1 plus D2 into 2 to the power minus 2 plus Dn into 2 to the power minus n. And the output voltage can be written as I0 into R1 VR into RF upon R multiplied by digital input. So using this formula we can calculate the output for any binary input. For example, if we take RF and R as 1K and digital input as 1101, the final output will come out to be, and the reference voltage 15 volt. Then the output will be 15 multiplied by R 1 upon 1, that is unity. Then D1 1 multiplied by 2 to the power minus 1 plus 1 multiplied by 2 to the power minus 2 plus 0 multiplied by 2 to the power minus 3 plus 1 multiplied by 2 to the power minus 4. So it comes out to be 15 multiplied by 1 by 2 plus 1 by 4 plus 1 by 16. So this is the output for binary input 1101. So in this way we can easily calculate the output for any binary input provided we know the reference voltage or the full scale voltage and the resistance of branches. So it's quite a simple and easy circuit to calculate the analog output for any digital input, but the basic drawback is the total number of resistors and the range of resistors required. This circuit requires a large number of resistors, means for higher bit input it requires 2R, 4R, 8R up to 2 to the power nR. So for larger inputs the range of resistance requirement is quite high, which makes this circuit quite unpractical to design, and that's why we use another circuit called as R2R ladder. Before that we will take an example. Consider the full scale output as 7 by 8 VR. The step size is 1 by 8 VR and the full scale value can easily be converted to number of steps multiplied by step size multiplied by 2 to the power n minus 1. So this is the staircase value for the digital input. Okay, so now we move towards another R2R ladder DAC. In weighted resistor DAC, we have checked one drawback, that is it requires a large range of resistors for higher bit data, because it requires different type of resistors, 2 to the power 1R, 2 to the power 2R and similarly 2 to the power nR. Hence, we require a circuit which consists of only two types of resistance. So in R2R ladder, we require only two resistors, R and 2R. That's why it is called as R2R ladder. Here the reference circuit is such that the overall combination of this resistance will comes out equivalent to R. You can see here that this 2R and 2R in parallel giving it R. Then this R is in series with this R, 2R. Again 2R and 2R in parallel giving R. Again this R in series with this R to give 2R. Then this 2R, 2R parallel giving out R. And this continues till the last point giving the overall value R. Now we move towards KCL approach. We can see from here that I1 plus I2 plus I3 plus IN, that is I1 B1 plus I2 B2 plus I3 B3 plus IN Bn is equal to I0. Also, from this resistance division, we can clearly see that if the resistance is doubled, the current will be divided by 2. So, the input current I1 we can say that the current is divided such that I1 is equal to 2I2. Now this 2I2 is again divided into two parts such that 2I2 equal to 4I3 and this 4I3 is equal to, so we take this relation and put it here like I1 B1 plus, for I2 we write I1 by 2, for I3 I1 by 4, similarly for IN 2 to the power n minus 1, and we sum it by taking common I1 and we take I1 as V reference upon I1 as V reference upon 2R. So the combined equation will be V reference upon R, B1 by 2 plus B2 by 2 square, similarly Bn by 2 to the power n. We substitute this value into final V0, which V0 is equal to I0 into R, which comes out to be minus V reference into B1 by 2 plus B2 by 2 square plus B3 by 2 cube, similarly Bn upon 2 to the power n. So in this way we can say that works in a similar way as weighted resistor, but it requires only two type of resistance, whereas weighted resistor requires a range of resistor based on the size of digital input. Now we move towards another technique, that is A to D converters. We start from the first one, that is counter type A to D converters. In this circuit we use a comparator, 741 IC op-amp IC as comparator, an AND gate, a counter divided by 256 counter, a control circuit to reset the complete circuit, an 8-bit latch to generate 8-bit digital output, and a DA converter. So the control circuit resets, initially the control circuit resets the complete circuit, that is counter, latch and every block before operation. Now when the analog input is applied, it is higher than the initial DAC output, which is 0. So the output of comparator is 1, making the AND gate on when the clock comes, and thereby the counter advances its state and generating the output compared to the analog input. When the DAC output is greater than analog signal, the comparator output 0, then the AND gate becomes 0 and there is no clock. So the counter stops and the control circuit store the counter value in latch, generating the 8-bit digital output and reset output for new analog input. More time to convert analog to digital, because after each clock the counter resets and starts from 0. So the basic drawback is that the conversion time increases with the magnitude of analog input. We can see that the waveform of this, for example, if we take an example of 1001, then the conversion starts, and once the digital value increases, then the analog input, the counter state again reaches to 0. And for next value, it again starts from 0 and count to next value. So it requires large conversion time. To solve this problem, we use tracking type A to D converter. Here, we use the same logic, but we use an up-down converter, that is both up and down converters. If the output of comparator is 1, then it uses up converter, and when the output of comparator is 0, it uses down converter. So instead of divide by 256 counter, it uses 8-bit up down counter. All else circuits are same. So when the analog input is greater than the DA converter output, the counter advances, that is counts in the upward direction, And once the analog input is less than DAC output, the counter count in downward direction, and hence it never resets, making it faster than the counter type ADC, because it never reset after its each sample, and it tracks the analog input, that is count up or down from its last count. So if the initial analog input is greater than DAC output, it works as up counter, and if analog input is less than DAC output, it works as down counter. So it always tracks the analog input. This is the sample output. If we take an analog input, it starts as counting, moves as up counter, and once the DAC output increases analog signal, it down count, and this procedure continues. So the conversion time of this type of ADC is lesser as compared to, and the maximum conversion time is 2 to the power n minus 1 clock cycles. Next is flash type converter. The flash type AD converter is the fastest type of AD converter. This type of converter utilizes parallel differentiator comparators or parallel op-amp, which compare the reference voltage with the analog input voltage. The main advantage of this type of converter is that the conversion time is quite less. But there is a disadvantage also, that for n-bit converter, it requires 2 to the power n minus 1 converters. It also requires 2 to the power n resistors and a priority encoder. So we take one circuit of 3-bit flash type AD converter. For 3-bit, it requires 2 to the power 3 minus 1, that is 7 comparators, 2 to the power 3, that is 8 resistors, and 1 priority encoder. So we move towards the circuit. This is a 3-bit flash type A to D converter. It requires a priority encoder. We can see here 7 comparators and 8 resistors. The whole reference voltage is divided into 8 equal voltages by these 8 resistances, such that starting from VR to ground, from first resistor it is VR by 8, then 2 VR by 8, then 3 VR by 8, and similarly last 7 VR by 8. We can start from the top, VR minus VR by 8, that is 7 VR by 8. 7 VR by 8 minus VR by 8, that is 6 VR by 8, and similarly VR by 8. So it divide the full scale voltage into 8 equal parts. The positive input is connected to the analog input. So there are 7 inputs from 7 comparators, and the x0 is equal to 1. So this is the truth table with 8 inputs x7 to x0, and therefore 3 output d2, d1, d0. So if the input voltage is less than VR by 8, all comparator outputs are 0, x0 is 1, and the output 0 is encoded at the output, that is 0, 0, 0. If the input voltage is greater than VR by 8 but less than 2 VR by 8, then the output of first comparator will also be 1, that is x1, x0 both are 1. Then as it's a priority encoder with MSB having higher priority, so 1 is encoded giving 0, 0, 1. Similarly, if the output is between 2 VR by 8 and 3 VR by 8, then x2 is also 1 and 2 is encoded as 0, 0, 0, And similarly, if the output is greater than 7 Br by 8, then X7 is also 1 and 7 is encoded as output, that is 111. So, this is very simple circuit with priority X7 as highest and X1 as lowest, and they directly convert the analog input to binary output. So it is fastest circuit, but the cost and complexity of this hardware is quite high for larger input voltage. Next is dual slope A to D converter. Here we require a comparator, an integrator, a control logic and a counter. Initially, switch S2 is closed to discharge this capacitor, and during charging process, switch S1 is connected to negative voltage, making this capacitor charge towards 1 upon V upon RC. Once this capacitor is fully charged, the peak time to charge this capacitor considering T1 as 1 upon RC. Once the capacitor is fully charged, the counter starts count to peak value. So once the capacitor starts charging, the counter starts counting in the upward direction and reaches peak. Next is the discharge process. During second phase, the circuit is connected, switch S1 is connected to V reference, and the capacitor starts discharging with reverse current, and the counter again starts to count with a slope of V reference upon RC. Consider as the discharge time T2 and charging time T1. Then we can write here as for T2, V peak upon T2 is V reference upon RC. Comparing equation 1 and equation 2, we can write here as T2 is equal to T1 into V reference upon RC. Since V peak upon T1, V peak is equal to T1 multiplied by VA upon RC is equal to T2 multiplied by V reference upon RC. From here, we can write as T2 is equal to T1 into VA upon V reference as given here. As T1 and T2 are proportional to the number of bits of counting, so we can write as N equal to N reference into VA upon V reference. So dual slope ADC is also used to convert analog to digital, and it is highly accurate because its performance is dependent on RC values. Next is successive approximation ADC. It is the second quickest A to D converter after flash type, and it has fixed conversion time independent of magnitude of analog input. For an n-bit ADC, it requires only n clock cycles. It again requires a comparator, a control logic, output register and MSB. Control logic resets the complete circuit. During first clock cycle, the MSB is set to 1 and DAC generates an output proportional to this input. For example, if we consider an analog input VA of 1101 and in first clock cycle the output VAX is 1000. When this output is compared with the analog input 1101 and this is 1000, the comparator output is high. If the comparator output is high, then the next bit is also Next bit after MSB is also set to 1. So in second clock cycle, VAX it becomes 1100. Again it generates an analog output VAX and compare it with the input. And in third case also, in first case, VA is greater than VAX. In next case also, VA is greater than VAX. And in third case also, VA is greater than VAX. So it again makes next input high. And once this value becomes greater than, once this value becomes greater than analog input, it resets the same MSB and set the next MSB generating VAX equal to 1101. And in this case, VA equal to VAX, the conversion stops and end of conversion is equal to 1. So after fourth clock cycle, we get the analog output equal to analog input. Analog output VAX equal to VA. So this is the overall process of successive approximation type. I hope these all the methods are quite clear to all of you, and by this I am going to end this topic of A to D and DA to A converters. Thank you all.